All right, class, we're gonna get started. Okay, so today we have a little bit of ground to cover. We're gonna cover lecture 22. So we're gonna talk about control charts, or basically how we can do quality control for process variation. Then we're gonna talk about at least the beginning of lecture 23. We're gonna talk about different statistics like the fraction of defects within a process with a similar kind of approach based on control charts. And then at the end of this lecture, we're going to go over quiz 6. And as a reminder, quiz 6 grades went back yesterday, so you should have seen them. I'm using Gradescope for returning those to you, so you should see it there. And the rubric tells you, basically gives you step-by-step of what I was looking for, but we'll go through that at the end of today's class. Any questions before we get started today? Okay. Then we'll go into it. So in last lecture, we talked about control charts for process location. And by process location, we mean the location of the mean, basically, or like the central tendency of that process. And we discussed this in terms of what we called an X bar chart, right, where we plotted X bar, or the sample mean, as a function of time. And then we look for the, what we're on the lookout for then are when the X bar, our value that we computed, the sample mean that we compute on any given day of running that process, if it goes outside the upper or lower control limits, then that indicates that we potentially have a problem. But there are other characteristics of a process that we may want to track. And so we can construct other charts. So just like that chart that we talked about on Monday was called an X bar chart. We're going to first talk about, for process variation, we'll talk about an S chart, as in sample standard deviation. We'll also talk about a P chart, for example, for some probability of some factor. And there are many other examples of this kind of chart that could be used to track process variation. And what we'll see is that the approach is very similar, right? So the approach for charting, for example, process variation is going to be very similar to the approach that we use for charting process location or process mean. We're just going to be using essentially different statistics, right? We're going to use a different distribution in order to compute the upper and lower control limits for process variation. And then when we look at other process attributes, we'll see that we use different distributions as well, but otherwise it's more or less the same kind of idea, right? So I mentioned earlier that so quiz 7 covers essentially what we've done since the material was on quiz 6, right? So it covers material on our response surfaces, our graphical representation of experiments and response surfaces, as well as this quality control information. But all of this builds on the things we've been talking about all semester. So for example, at the start of lecture 23, when we look at that example, we're going to talk about binomial, right? Binomial distribution, which we talked about on the first day of this class. We're going to talk about that in the last piece of the lecture of this class. We'll talk about Poisson. We'll talk here about standard deviation. We've already talked about normal distribution in this section. So we're more or less using all of the concepts that we've discussed all throughout the semester in order to understand these kinds of things. Okay, so, and again, this is going to be based on chapter 16 of that DeVore text, which is up on Canvas. So when we're talking about process variation, we're talking about some measurement of how much the values that we measured, or the sample that we measured about that process vary on a given day. There are different ways of doing this kind of testing. We're going to focus on testing based on sample standard deviation. So we'll be plotting what's called an S chart. You could also do this based on range. And in fact, this kind of testing for process variation based on range may be more common. It's certainly the older method for doing this. And so you will encounter it. You may encounter this method. In that case, you construct what you might call an R chart. We're going to focus on S charts and charting for sample standard deviation or process standard deviation, because it's more robust statistically than looking at just the range, but note that similar kinds of methods would apply if you're doing a range chart. So as an example, we'll again do this by example. We're going to say that we have measurements of stress resistance of plastic sheeting are given in our data set. We have 22 samples, 4 observations for each sample, and the samples were obtained at equally spaced times. So we have the data that we need in order to construct a control chart. And now we're going to, so we load that data in, we're again using pandas. And now we've taken that data and we're adding in, similar to what we did last time, we're adding in columns for, in this case, not the sample mean, but just a sample standard deviation and also the range that was observed for each observation period, right? So in this case, we're not specifying necessarily that the observations were on different days. Maybe it was done over a period of weeks, or maybe it was done over a period of hours or something. But in any case, we have a number of different observation periods, and we have 4 measurements per observation period, right? And then we're plotting, we compute a standard deviation and range for each one of those. And again, note that we're computing, this is a sample standard deviation. So we've done this using the pandas function for sample standard deviation, which assumes that it is a sample, and therefore the delta degrees of freedom is equal to 1, meaning that we're dividing the sum of squared errors by n-1 when we use that function. This is distinct from the NumPy realization, remember, that we talked about a few times, that was on one of the quizzes, where NumPy assumes that you're trying to compute the population standard deviation and that the denominator in your standard deviation expression is n. And so in that case, we had to, if we're trying to compute sample standard deviation, we have to specify delta degrees of freedom. Here, we did not specify it because the default is already for a sample. So with this data, we can then construct what we call the S chart. Again, just as for the X bar chart, there are, we could either construct this chart assuming that we have some, let's say, historical data on what the population standard deviation is, or in this case, we're going to proceed assuming that we don't know what the population standard deviation is. And so we're going to have to estimate that population standard deviation. And then, as I mentioned, we can do this in order to construct the control chart based on the sample variance. We could do control chart based on standard deviation or ranges. In this case, we're just doing a control chart based on standard deviations. So in this case, we need to, because we're not given the population standard deviation, we need to estimate the population standard deviation. And the way we're going to do this is basically just take the mean of all of the individual standard deviations that we have obtained. And so our estimate of the, so our S bar, our average standard deviation, is just the mean of all of the individual measured standard deviations. And using that estimate of S bar, we're then going to have to correct that. So just like we did in the previous lecture, if you remember, we had a correction for how to go from S bar to the population standard deviation, sigma. It was based on a correction factor we called A sub n, where n is the number of measurements that we made. This is based on the gamma distribution. It's similar, which is related to the chi-square distribution, which we used in lecture 17 for inferences about variance. But in this case, we can just think of it as a correction factor that allows us to go from S bar to the actual, or to a better estimate of the actual population standard deviation. And so in this case, we're using, again, that A sub n, that correction factor. And this is what we would define, what we're going to define as the upper and lower limits of the of our upper and lower control limits for our standard deviation of our process, right? So it's based on S bar and this factor, this correction factor A sub n. So, and then we're going to use these in a very analogous way to what we did for the X bar chart that we looked at last time. So one thing to note here is that if you look at this lower control limit expression, if we have n less than or equal to 5, it turns out that based on the value of an for n of 5 or smaller, you'll end up with a negative result for the lower control limit, or negative lower control limit. And that doesn't really make sense because standard deviation is always positive, right? Standard deviation is the square root of the variance. Variance is always positive. So our standard deviation is always positive. And so it wouldn't make sense to have a negative lower control limit for your variance. And so it's common practice that if n is less than or equal to 5, or if the lower control limit ends up negative, then we just set the lower control limit equal to 0. And we'll see that implemented with logic in the code with an if statement in the code that follows that implements this, but it's something you can do manually as well, right? If the lower control limit is less than 0 and we're considering standard deviation, that doesn't make sense. We're just going to set it equal to 0. And again, then the other note here is the correction attached to S bar is because we're estimating sigma from the data. We don't actually know the population standard deviation. We're trying to estimate it. And then this factor an is calculated as before, so as we did in lecture 21. So this is how we calculate that an. In this case, an is 0.921 based on 4 measurements, right? N is equal to 4. N is, so a note, in this an, something to keep track of, something that could be easy to make a mistake on. N in that correction factor, a sub n, is the number of measurements we made at a given time point. So in this case, we had 4 measurements for each observation period. And so n was 4. Okay. So even though we had measurements over 22 observation periods, at each one of those observation periods, we only had 4 measurements that we're using to estimate the standard deviation. And so we called our n equal to 4. Yep. So our k, yeah, so we had 22 periods of observation, that's correct. And we have 4 observations per period. Yep. So n here was 4, and k would be 22. Yeah. So using that a sub n, which we can compute, I mean, this is how we compute it in Python. We could also look it up if we were given a table of a sub n. Then we compute our S bar is just the mean of all of the individual estimates of the standard deviation. And then this code block implements what we've outlined, just scrolling up, in expressions 2 and 3 then, based on S bar and a sub n. So we are then estimating the lower control limit as S bar minus 3 S bar times that correction factor, which was computed from the value of a sub n that we computed from a sub n. We have an if statement here that says if lower control limit is less than 0. So if we have a nonsensical lower control limit, because we know standard deviation is always greater than 0, then we just set the lower control limit equal to 0. The same thing for the upper control limit. This is again just implementing that expression from above. And then we are printing out what our lower and upper control limits are. So in this case, our upper control limit is 5.3, lower control limit is 0. And then again, we're constructing a plot very similar to what we did for the X bar chart, right? Except the difference is that now we're looking at, we call it an S chart because we're looking at the sample standard deviation. So we're going to plot our data as a function, right? Our standard deviation for each individual day as a function of, or for each individual observation period as a function of the number of observation periods with our upper and lower control limits. And this is our result. So now the red dots on this plot indicate the standard deviation from that observation period, right? So standard deviation, each one of these dots is standard deviation of the 4 measurements in that observation period. The lower control limit, which is 0, right? Because we had computed a value that was less than 0, but we fixed it to 0 because it can't be negative. That's our lower control limit. And our upper control limit is the dashed line at the top. And so from this chart, we can then use this chart to estimate whether or not this process is in control based on the standard deviation. So is this process in control? If you think, who thinks this process is in control? Raise your hand. Who thinks this process is out of control? Yeah, good. So why is it in control? Anyone? Yeah. It's within the two control limits, right? So we do not have, so all the evidence here indicates that this process is in control, okay? I think the last example in lecture 23, we will actually see an example where it's out of control, but all that means is that one of the dots is outside of the control limits, okay? Yeah.
Would you be able to say it's out of control if, for whatever reason, the standard deviation?
Would we be able to say it's out of control if all the standard deviations were on one side of the bar? Well, first of all, in this case, it's not possible because this is the mean. This is S bar. I mean the corrected S bar, but this is our overall. This is based on our data. So it wouldn't be possible for us to have all the data on one side. But if we knew what the sample standard deviation should be, right, then it could be possible to have all of our samples on one side of the bar. And that's where you get into, so it could be possible to have all of our sample standard deviations on one side of the center line, and but still within our upper and lower control limits. That is theoretically possible. In that case, it would not have failed this test. It likely would fail another supplemental test analogous to what we would do for the X-bar, what you might do for X-bar control charts. It's beyond the scope of what we're going to cover in this class. As far as here, we're just doing an introduction to control charting, just so you know the concepts and the basic concepts and how it applies to what we've done in the past, but you can go quite a bit further than that. But yeah, it's likely your process would be out of control if all your data were on one side. Good question. All right, any other questions on this? So this is actually all we're going to say about S charts, right? So all of the SI, all of the sample standard deviations are within the control limits. So the process appears to be operating in a stable way. So again, it's very directly analogous to what we did for the X-bar charts. Any questions on this? Okay. All right, then we're going to move on to lecture 23. And what we're going to see is, again, a lot more of the same kind of idea of what we've seen for X-bar charts and for S charts. But now this is for different process attributes. In a sense, this is a little bit analogous to what we did for hypothesis testing, right? We spent a lot of time talking about hypothesis testing for sample means, right? Where that comes from, what the distributions underlying that are, how to compute it, how to use it. And then when we got to, for example, hypothesis testing or confidence intervals about population variance or standard deviation, that was a much briefer discussion because we'd already laid kind of the foundations. We just had a different distribution that we had to consider. It's very much analogous here, where we have already kind of laid the groundworks in last lecture on X-bar charts. And so now for these other charts, it's more or less, it's the same concept, different statistics, different ways of computing the upper and lower control limits based on what the relevant distribution is, what the relevant statistic is, but it's the same basic idea. Okay, so for attributes, so what we mean here would be, for example, if we have a classification of an item coming off of an assembly line or something as defective or non-defective, or a sample as being good, like within spec or out of spec, then we have this binary decision, right? That could be an attribute about the sample. And in that case, we're going to construct a control chart based on the binomial distribution. The other way that we could define an attribute is based on, for example, a number of defects, right? So this could be a number of defects within a sample, number of defects within an item. In this case, and then we're recording a number of defects as a function of our observation periods. In this case, the relevant underlying statistic would be the Poisson distribution, right? So an example for a number of defects, like if we were looking at LCD panels or something, right? There are a certain number of defects that are allowed essentially within an LCD panel on a TV or a computer screen. And that would be, if we were charting that in some process, or we would use Poisson distribution because that's the relevant underlying distribution. So we're going to start with the P chart, which is for the fraction that are defective within a given sample. So as our example here, we have, let's say we have a sample of 100 ceramic crucibles on 25 successive days, right? So our observation periods are on successive days, and each crucible is inspected for defects. And then we're looking for the number of defective crucibles as and we have a certain number of defective crucibles. So then we're then going to look for the proportion, and then what we're interested in tracking here is the proportion of defects on any individual day. So we read in that data, and now we're going to then compute the proportion that is defective for each individual day. So there are 100 in each sample. So the proportion is really just this 7, right, divided by 100. And so now, very analogous to what we had for X bar control chart and S control chart, now for this P control chart, or the proportion defective, we have our basic data is this P hat, right, the proportion defective versus the number of days. So we're going to be plotting that. And the question now is, how do we construct the upper and lower control limits for this data? And since we know that a binomial process should follow this binary process should follow binomial distribution, we're going to use what we know about binomial distributions to construct those upper and lower control limits. And so what we're going to say is that the proportion, right, our analogous kind of 3 sigma limits are going to be given by P plus or minus 3 times square root of P times 1 minus P over N. So, so we'll use that as our upper and lower control limits. There's an implicit assumption here in writing it this way. Does anyone know what assumption we're making? Yeah. So one assumption is that we actually know what P is, and we're going to talk about how we estimate P. We're going to use the overall grand mean in order to estimate P is. But yeah, we're assuming that we know what P is. So, and that could be, we know P based on, we know the proportion defective based on how this process is run in the past. And we're just going to use that historical data, just as we did for X bar and S charts. Or we could estimate P based on, in this case, we're going to say we'll use P hat as the average of all of our estimates of the proportion defective. But there's another assumption that we've made here. Yeah. Enough successes and fails for what? Enough successes and fails that we can use the normal distribution, right? So this is assuming that we can approximate the binomial distribution using normal distribution. And then you'll see that this, this result here is the standard deviation for a large sample when we're talking about a test of proportion. This is often the case if we're running this on successive days and we have a lot of samples that we're drawing from. And so this assumption that we can use the normal distribution is generally pretty good. But what that means is that this equation 1 here is really just saying that we're constructing a 3 sigma control chart, which is what we've been trying to do, right? So we're saying that our upper and lower control limits are going to be given by P plus or minus 3 times the standard deviation, assuming that we can use a normal distribution to approximate the binomial. So beyond the scope of what we're going to talk about here, but if you did have a case where you have so few successes or fails that this was not applicable, then you could go in and use a binomial distribution to try to make a correction. And the textbook chapter that I put in Canvas does discuss this a little bit, but we're not going to go into that here. Okay, so this is now our upper and lower control limits for our 3 sigma chart based on P. So again, we need to know the overall proportion of successes or failures, in this case failures. And we're going to do that by computing the mean of all of the individual failure proportions, right? So PI, so again, this would be like taking these P hats are given in this column here. So basically just taking the average down that column is going to give us our big grand mean P hat. And then our upper and lower control limits are given by that equation 1. Again, I should note that if the lower control limit ends up less than 0, we just set that lower control limit equal to 0 because we cannot have a negative proportion of failures. So the code here implements those equations, right? So we take the data, we compute P bar, it's just the average down that entire column. So we end up with a P bar of about 0.061. We construct the limit is our 3 sigma limit, assuming that we can approximate binomial as normal, using the expression for the standard deviation of that approximation that we discussed previously. And then we have our upper and lower control limits. Again, we have this if statement here that's just checking whether or not the lower control limit is less than 0. And then we plot it the same way. So now we have our upper and lower control limits. We're going to plot a control chart in exactly the same way. And this is our result, right? So for our given data, we have our center line here is P bar. That's the overall mean of proportion of success or failure. Our upper and lower control limits are those 3 sigma limits. And again, we can see that all of the, each individual red dot rather is P hat, or our estimate of the proportion of failures from a given day. And again, we can see that all points lie within the upper and lower control limits, and it looks like our process is in control. I know I'm going faster over this than I have over X bar and even the S control charts. Is that okay, or am I? Yeah, okay. Because again, we have seen this before. Okay, so that's a P chart, right? So it's the same idea as the X bar chart, same idea as the S chart, but it's just a different type of control chart that we can use to track a process. If we did know what the proportion of failures should be for our process, and now note, this is not, so if we did know what proportion of failures we expect to see in our process over a normal period of operation, so if we knew what P was, then we could use that instead of P bar. But we can also, in this case, we estimated it directly from the data. And again, another thing to note is that, maybe in this process, this is a ceramic crucible manufacturer. Maybe the acceptable failure rate is, somewhere is 0.15, right? So it might be that I can tolerate 15%. That seems pretty high, but it might be that I could tolerate 15% failures and still have an economical process, right? The fact that that is the tolerable limit doesn't actually enter into this control charting. Control charting is about what is typical for my process. It's not necessarily related to what is acceptable for my process. Does that distinction make sense? Okay. Because previously, when we talked about proportion of failures, we often talked about it in reference to what the acceptable limit was, right? So we would ask questions like, let's say we have this crucible data. We saw that the proportion failure was, about 6%. We had a certain number of trials, and we asked questions about, can we say, we did a hypothesis test, for example, to say, can we say with 95% confidence that our true failure rate is less than the acceptable limit, right? And there we use the acceptable limit in order to construct that hypothesis test. Here, we're not interested in whether or not the result is acceptable. We're just interested in whether or not the result of our process is stable. And so we construct our limits based on what the process looks like historically. And we're just looking to see if we're veering inside or outside of that, of those limits. Okay, so there's a bit of a distinction with what we've done in the past. Okay. So then, since we're going through a little quicker, and I do want to put this onto your next homework. I do want to put all of this control charting onto your next homework. We will go over the last topic in lecture 23, but it'll also give us a little bit more time to talk about, to do review next week on Monday and Wednesday in the class, okay? As long as it's okay with everyone here. All right, so the final example is going to be looking for, is going to be when what we're interested in is the number of defects that we have within a process, rather than the proportion of defects that we have within the process. So a subtle difference. But let's say that we're manufacturing metal panels, and there are some flaws in the finish of these panels, right? And we want to set up a control chart for the number of flaws. So again, it's a control chart. So this means we're going to have the same thing. We're going to have some estimate of what the center is and what the upper and lower limit are, and we're going to plot our number of defects and see if it lies inside of those bounds. The only difference here is that we have a different distribution, right? We have a different underlying probability distribution that governs the number of flaws, and here it's going to be Poisson, right? So Poisson distribution, just as a review, we had a number of things that were necessary for application of Poisson. So we have to know that there's some mean number of events that are going to occur within an interval of time or a volume or an area or something. So it could be like, you know, number of earthquakes over a period of time. It could be number of defects within a panel. It could be number of trees within a square kilometer or a forest or something. The occurrences need to be independent, meaning that one occurrence does not affect the other. So in this case, we would have to have the case that one defect in the panel doesn't affect the probability that there's another defect in that same panel. The effects should occur at a constant rate or density, a constant average rate. So there are fluctuations around what that rate is, but overall rate should be constant. Two events can't occur at the same instant or at the same location, and the probability of an event should be proportional to the length of the interval or the size of volume or area. Basically, if we have a longer interval, we're more likely to have an earthquake, right, along the Wasatch. Or if we have a larger area of panel, we're more likely to have a defect. So if these conditions are met, and they often are for randomly occurring events, then we can use, or at least approximately are for randomly occurring events, then we can use Poisson. So just this is a review of some information that we had before. We talked about these distributions, but let's say we have, we're using Poisson distribution to look at earthquake recurrence rates. And if we know that the recurrence rates for large earthquakes are once per 350 years, then we can use Poisson distribution to calculate the probability of a certain number of quakes within a 350-year period. Right, so the average number is 1 in 350 years. And so we can find the probability of a certain number of quakes within that period. So Poisson distribution is what's going to govern when we're talking about number of defects. Then Poisson distribution is the governing statistic, and we're going to use that to construct our upper and lower probability limits. If the random variable has a Poisson distribution, then the expected value is lambda, and the variance of that process is also going to be lambda, where lambda is the average occurrence rate. So in our example, lambda is the number of flaws per panel, right? So the average number of flaws per panel. And so again, just like in the previous example, in most of these examples, like we may not necessarily know what the overall average value of lambda should be, right? Maybe we don't have access to historical data and we need to estimate it from the data set. So a reasonable approximation would be the average number of flaws within our sample, within our data set. So we use that as our lambda hat. And so then our upper and lower control limits on our chart, again, these are going to be 3 sigma upper and lower control limits. We're going to be the overall mean number of flaws that we saw. I guess it should be lambda hat instead of x hat, but this would be the overall mean number of flaws that we saw, plus or minus 3 sigma, where sigma is just the square root of, again, the average number of flaws that we saw. Would be our upper and our lower. Again, if lower control limit is less than 0, we're just going to set it equal to 0. Yep. Sorry. This should be bar lambda. Let's make this correction. And this should be lambda in here as well. But the square root of lambda bar is sigma for this process. Okay, because the variance for this process, our estimate of the variance for this process is lambda bar. And the standard deviation, or sigma, is the square root of the variance. So this square root of lambda bar is our sigma for this process. So these are upper and lower, these are 3 sigma upper and lower control limits, because this whole thing here is sigma. Does that make sense? Yeah. Thanks. Yeah.
So you just find lambda bar by averaging the number of flaws per panel.
If you're not given it, right? So if we knew what lambda should be, right, for historical data on running this process many times, then we would use that, right? But if we didn't know that and we had to estimate it, then we would just estimate it from as the average number of flaws per panel. That's correct. Yep. So we're going to now apply this to our data. So we'll take our data, again, in this example 2, where it is for each individual measurement period, it's the number of flaws that were observed within that panel. And what we find is that, so there were K is equal to 24 observations, right? 24 panels. Our lambda was 9.8 flaws per panel. So our overall lambda bar is 9.8 flaws per panel. And now we're going to plot that data in a control chart in the same way that we have before. Again, note we have this, if lower control limit's less than 0, we set it equal to 0. We're doing that in this case because, again, it doesn't make sense to have less than 0 flaws per panel, right? And so when we plug that into the formulas that were given above, we end up with an upper control limit of 19, lower control limit of 0.4. And now we're just going to plot our upper and lower control limits, right? The same way that we have. And so here's our control chart for number of flaws. So this is lambda bar in the middle. This is plus or minus 3 sigma, right? For these upper and lower control limits, where sigma is the square root of lambda bar. In this case, we can see 1 point is above upper control limit. So is this process in control at all times? No, it doesn't look like it, right? It looks like at this day 15 or sample 15, it looks like our process may have been out of control and there may be a cause that we have to evaluate. Yeah.
So if we just have one value above, do we say the process is out of control just period, or do we just say on day 15 the other day?
Yeah, this would be evidence that on day 15 it may have been out of control. It looks like it's likely in control on other days, but really this control charting is not about saying what was wrong. It's just about flagging that something might be wrong. And so this just tells us that something might have been wrong on day 15. Now there's a chance that something wasn't wrong, right? There's a chance that everything was actually fine, right? That chance is like 0.3%. That, right, remember our 3 sigma limits mean that there's only about a 0.3% chance that we see a result like that, but the process was actually in control. So it indicates there's likely a problem on day 15, but it doesn't tell us what it is. It doesn't even tell us for certain that there was a problem on day 15. This is really just saying, hey, go take a look at what was going on then. Yeah. Okay. So sample number 15 is outside the control limits. In this case, that cause may have had some attributable cause, which would be that the slurry was too thin, had a low viscosity. So we'd call that an assignable cause. And then if that's true, it would be reasonable to then redo the calculation by removing that, right? So if we know that there's something wrong with this data and we're trying to estimate lambda hat, then this data point, this outlier is dragging our estimate up, right? And so, you might want to go back and redo this using with that data point removed. It would be reasonable to go back and do that. In this case, we haven't. We're leaving it here for our discussion. And that concludes our discussion of control charting as well. Any questions overall on control charting, the concept behind it, or how to do it, how to interpret it? Okay. Then that also concludes our new material for this class. So Monday and Wednesday will be review. Congrats to you all. So Monday and Wednesday will be review, and then and this will be part of the material that's on quiz 7.